A new study combining multiple telescopes of different wavelengths has successfully made the most precise measurements ever undertaken of the total amount of radiation hitting the Earth, finding that the planet's being bombarded by about 6 photons per square metre every second. The findings, reported in the Astrophysical Journal, show that most photons originate as expected from the Sun. However, the study also found a significant percentage come from other stars, energy beams being blasted out by supermassive black holes as quasars, and through light being reflected by cosmic dust. In fact, it turns out that about 10 trillionth of your suntan this summer probably comes from beyond our galaxy, having travelled across the universe for billions of years before finally ending their existence when they collide with your skin. The study's lead author, Professor Simon Driver from the University of Western Australia, says this is the most detailed and comprehensive study ever undertaken of light coming from beyond our galaxy. In fact, previous estimates of this radiation have varied by a factor of 10, and the new findings indicate cosmic dust could be causing a significant effect. The new research focused on photons ranging from ultraviolet through visible light and into the infrared, the range where most of the energy in the universe is produced, other than that coming from cosmic microwave background radiation, the leftover heat from the Big Bang 13.8 billion years ago. Driver and colleagues found that the Earth's being constantly bombarded by about 10 billion photons per square metre per second from intergalactic space, known as extragalactic background light. The authors measured this ambient radiation from the universe over a wide range of wavelengths by combining deep images from a flotilla of space telescopes. These included NASA's Galaxy Evolution Explorer and the Wide Field Infrared Survey Explorer telescopes, as well as both the Spitzer and Hubble space telescopes, the European Space Agency's Herschel Space Observatory, and Australia's Galaxy and Mass Assembly Survey, to make the most accurate measurements ever undertaken of extragalactic background light. The study's all part of an ongoing research program to better understand the evolution of energy, mass, and the structure of the universe. Driver says the research program examines how the cosmos went from the smooth distribution of atoms in the early universe to the emergence of the periodic table and the multitude of stars, galaxies, and galaxy clusters we see today.
We've brought together data from a whole array of telescopes, in particular 3 or 4 NASA space telescopes and an ESA space telescope, all the very, very deep field data over quite a wide wavelength range. And we've used that to measure all the radiation that we're receiving from extragalactic space. So in a way, we're making a measurement of all the energy being produced in the universe over all time.
And what did you find?
Well, we found quite a lot of energy, and I think the thing that is perhaps most humbling is we also have a model that seems to explain it as well. And so we've made the measurement. We found that there's 3 particular energy pathways. There's the star formation pathway, the same process by which the sun burns. There's the quasar pathway, which is the accretion of mass onto supermassive black holes. And there's the reprocessing of this energy by dust grains. And the models that we have basically give a very good prediction for the CBL. So it's kind of nice that it all comes together. We've managed to bring this data from a wide range of space telescopes and make this measurement at a much higher accuracy than ever before. And then we seem to have models that explain it as well. There's 2 main ways in which energy is produced. I mean, there's a multitude, but if you think of it in terms of the total amount of energy being produced, it comes down to 2 ways. One is star formation, and that's just nuclear fusion taking place inside the cores of stars. That's the clean nuclear energy we would love to understand and love to be able to replicate here on the Earth to solve our energy crisis. So
it's always 20 years away.
That's right. We always seem to be 20 years away. We just don't seem to ever get any closer on that one.
It's like quantum computers. It's the same thing.
Yeah, no, another one. Well, they said that about gravitational waves, of course.
Yes, point taken.
And so every so often you do get that surprise. But anyway, nuclear fusion produces about half of the photons that are generated after the Big Bang. The other half is coming from material that's been squeezed and sucked into supermassive black holes. So we believe the center of every galaxy has a supermassive black hole. Stars, gas, whatever material is gradually being drawn into these. It gets crushed, forming an accretion disk, and in that process, it generates an awful lot of energy. And before the matter disappears into the black hole, nothing can get out of a black hole. You do have a lot of energy release, and so half the photons flying around in the universe are generated by star formation, and the other half are generated by this quasar activity. And then just to make things a little bit more confusing, galaxies also contain dust grains. So this is just carbon and silica dust grains, and they tend to block some of that light. They then heat up, up, and then they glow at another wavelength.
When you break all that down, you also looked at photons of different wavelengths. How do those figures break down?
Yeah, that's right. So well, we looked in this study, we looked from the ultraviolet down to the far infrared. So going from wavelengths of 0.1 micron, which is much lower than the human eye can see, up to about a millimeter wavelength. That's where we believe most of the energy, most of the photons produced in the universe are being generated in that wavelength window, which is why we looked at that specific wavelength window. And you find at the very short end, you've got lots of the quasar energy coming out, and then through the optical, you've got the bulk of the stars producing photons, and that gives you one big hump in the optical wavebands, and then it sort of dips down a bit, and then there's a second hump, which is the dust that has a temperature of about 30 degrees Kelvin, and just re-radiates and glows with a black body spectrum that comes out of the far infrared wavelength.
Are you missing much by not going to higher and lower wavelengths?
Well, these are other active areas that we're not currently pursuing, but there is the X-ray background, and then there's the radio background. Estimates of those have been made, and they come in about 100 times lower. So at the moment, we think that out of all the backgrounds, the largest background by far is the cosmic microwave background, the leftover radiation from the Big Bang.
2.7 degrees above absolute zero.
That's right, exactly, yes. So 2.7 Kelvin. And that's still the largest photon bank of all. And then about 20 times lower is this extragalactic background light. And there's been a fair bit of controversy. Various people have made measurements before, a couple of filters here, a couple of filters there, using different methods. When you put the data together, it's a real hodgepodge, maybe a factor of 10 uncertainty in some of the measurements at some wavelengths. And so we decided it would be a good idea to sit down with all the data and process it in a very standard way. And when we did that, we got a beautiful curve that just looked right and had very, very small error bars. And we think some of the controversy as to why there might have been measurements, I don't want to say incorrect, but I guess I have before, is possibly because we haven't understood how much dust there is in the solar system, or the impact of maybe the Earth's atmosphere as well in our observations.
What's the next phase?
Yeah, well, the next phase for us is to try and break it up. So what we've done is we've sort of integrated along the entire line of sight, all the way from today back 13 billion years. We've added up all that energy. Now, what we want to do is to start breaking that up and say, well, how much energy came from 10 billion years ago? How much from 9? How much from 8? And so we can see how the balance between energy production between, say, quasars, star formation, and the impact of dust, how that's changed as a function of time.
That's going to tell you an awful lot about things like the epoch of reionization and when we entered the stelliferous age of the universe, things like that.
Oh, yes. Yes. I mean, I think having a complete model of the energy production in the universe, I mean, I guess we're fundamentally interested in mass.
Yeah, that's huge.
How did we get from the smooth distribution of atoms to things like stars and planets and black holes and so on? And every time there's a shuffling of matter, there's some energy produced. And so we want to follow the mass and measure the mass, and we also want to measure the energy, and then build a model that explains the build-up of mass and all the different types of mass, and see if we can explain all the photons that are flying around in the universe. And I'd say we now have the capacity to do that with these wonderful telescopes. I mean, NASA's various telescopes, which we've used, the Galax, the WISE, the Hubble Space Telescope, of course, and then the European Southern Observatory's Herschel Telescope as well, which gave us the far infrared data. So, it's been an absolute godsend to have access to these fantastic facilities and to be able to put them together. And in a way, I think astronomy is changing a little bit, that we're no longer just working with one facility as an individual astronomer, but we now have to look at the universe by tying together the data from all these different telescopes, even eventually including the radio and the X-ray as well.
Yeah, we're seeing astronomers who are optical astronomers collaborating more and more with radio astronomers and so on.
Yeah, absolutely. I mean, we're here at ICRA with a square kilometre array hopefully being built up the road in the not too distant future, and it just wouldn't make sense to just focus on the radio only. You want to combine that radio data together with all the other wavelength data that's out there, and I'm looking forward to find out about the LSST, the Large Synoptic Survey Telescope, which will be the next great thing in optical data, and trying to tie that together with the SKA will be even more powerful.
That's Professor Simon Driver from the University of Western Australia and the International Centre of Radio Astronomy Research.